Vinueza. I've been doing this for more than 15 years now, and I'm very happy to showcase and show you guys how is it that you can use ModelRisk. An introduction to ModelRisk applied to an energy model. ModelRisk is a product, is the flagship company from a company called Vow Software, which has more than 25 years of expertise doing QRA, quantitative risk analysis. And the software itself, I think it's year number 19. They were first consultants, and then they created these 3 parts of software programs. One is ModelRisk, that I think it has 18 or 19 years in the market. And also they have 2 other pieces of software called Tamara, which is for project risk analysis. And also they have something called Pelican. This is for enterprise risk project, enterprise risk management. So these are the 2 additional offerings that they have. We have videos showcasing these products too in our YouTube channel. So please visit us, subscribe. More than happy to have you there. Right. So who's us? Fairfield Group, as Jameson and Dan well introduced. So we do risk modeling and consulting services. And it's what we want to be is your partner in quantitative risk solution, right? We've been doing this. We have experts in the field, plus Jameson and Dan, they've been doing this for many years now. And we help our clients to derive the maximum value from their software investments. We have access to a network of experts, whether you are in the Middle East, in Brazil, in Latin America, or in the US, of course, in Europe, more than happy to help you. And if you want to contact you with some local resources that can help in our name. We have a lot of industry experience derived from all these contacts that we have in energy, infrastructure, financial services, manufacturing, etc. Some of our main logos and people that we work with during the years are here. And we're going to start now, right? So what does ModelRisk do? And ModelRisk do is mostly Monte Carlo simulation on top of Excel. I'm going to do a very quick Monte Carlo simulation explanation here, and then we're going to dive into the model directly. Yeah. So remember, Monte Carlo simulation, what is it and how is it that we apply it here? Because this is applied Monte Carlo. We're going to have a model, which is here in orange, right? We have our model logic that could be an NPV calculation, a cash flow, an estimation model, a budget model, in this case, a solar panel calculation model. And what we have to do, and this is how we normally, of course, we do Excel modeling, we need to set up variables, right? Input variables, these are our input variables that go into the model. You can have as many as you like. With ModelRisk, you don't have a number of, you don't have a limit in the number of variables. And then these variables, they're combined through some equations, with some mathematical operations, and then you have a result. And this result could be your NPV, your payback, your total cost, your cash flow, etc. So the main idea is that we're going to add in Monte Carlo simulation, we're going to add an additional layer, and this is the layer where we're going to replace potentially every one of the variables with a probabilistic distribution. This fact, when you replace this, replacing variables with distributions, right, generate ranges, right? And this is the key word here, right? We're going to have ranges. So instead of variable C being maybe, I don't know, 10%, now we're going to have a range between 3% and 11%, right? We're going to have a range. That means that every time that we run a simulation, right, we're going to fetch samples. Let's see, where's my cursor? Here you go, right? We're going to fetch samples for each one of the variables, right, for each one of the distributions, and they are going to come here. And the model is going to absorb those, and it's going to be recalculated many, many times, right? This is going to happen thousands of times, meaning that we're going to have, for the same model, thousands of slightly different results. Why? Because you see that the nature, the random nature of fetching the variables here is going to cause that. So at the end, we're going to have something like this, right? A table with results, maybe with 1,000, 2,000 results derived from the calculation of the model, and we're going to be able to draw it, to visualize it like a histogram. We're going to see that we have tornado charts, etc. So this is in a nutshell what Monte Carlo is going to do. It's going to add variables, add uncertainty to variables in the shapes of distributions. The model is going to be the same. The model logic is going to be the same. And then we're going to have thousands of results recalculated. And that's why we have this introduction to model risk applied to different industries, right? Because we want to show people how is it that they can very easily improve a model. And the model that we're going to see today, you will see it has like 6 cells, and we can get so much from it, from just knowing how is it that we can do it, right? Now, it's only simulation model risk. It's more than that. We have more than 130 distributions, 30 time series, copulas, and the graphical capabilities you will see are amazing. But we have also portfolio optimization. We have data viewers in the tool, and we have a simulation important management, key drivers, etc. Right? So let me show you model risk. So let's start with that, and then from there we go. Right? Let me close this. Here you go. So model risk, it's here. Here you go. Model risk, it's a tool that is going to be on top of Excel. You see here, it's going to be on top of Excel, and it has all these options there, right? That's the main idea of model risk. Through all this series of options, you will be able to select distributions, as I was saying before, update correlations, fit distributions, start simulations, and watch results, right? That's the main idea of the solution, right? So model risk, remember, sits on top of Excel. Why is that? Because the main idea is that you will be very productive when doing this, because you won't have to learn anything else, which is great, yeah, because you just have to learn how to model in Excel, which I imagine that you already know, and then you will be able to do it. Right? Now, I have this help here. Here you go. Now, this is the model that we're going to use. You see, it has total 9 cells. It's a very, very simple model, and one of them is not even a distribution. And what we're going to do, we're going to go one by one, understanding the different variables that you have in the model. How is it that you model them, and how is it they integrate together? Okay, that's what we're going to do. Now, how is it that you model a solar panel? And that was one of the challenges here, right? I'm not an expert in solar panels, right? So I had to study a few hours here to understand and to make it simple, right? I didn't want to have a super difficult model either, but something that it's simple to understand, but that at the same time it's easy to use and it's very applicable, right? That was the main idea. So one, how is it that you measure and how is it that you build these models? First of all, you have what we call MWP, or the installed peak capacities, the megawatts. You have a power output. You have the energy over time, which is megawatt hours. You have the number of sun hours, remember, because you have the direct application of the sun, and a performance ratio, right, which is the real world efficiency. And then what I did, I tried to do a very simple comparison with what would be with driving a car. So you have a simple comparison, like the installed peak capacity is the number of panels, right? It's like your engine horsepower, right? It's like theoretical capacity. Then you have the power output, which is your speed, right? The speed of your car, the energy over time, the kilometers or the miles that you have driven, and the sun hours is the time you drive. That's the main idea. So the real energy that you're going to pour into the system, right? It's going to be your installed capacity times the sun hours, because of course we need the sun here, right? Plus a performance ratio. Here you have a simple example. Let's say that we have 50 megawatts of peak capacity. We have 2,000 hours a year, which is a good number, right? A good number. Plus we have a performance ratio of 0.80. That means that the real energy that you will get from the panels is 80% of the theoretical one. Why is that? And we'll see, because we have losses because of temperature, we have losses because of dust, we have losses because of disconnection to the grid, right? And if we do this simple calculation, we will have like 82,000 megawatts hour a year, right? That's like 82 gigawatts. So how much is that? So for you to know, is if you have 82,000, right? In a typical, I don't know, US style consumption, or between European and US style, that's like a small power, a small city of between 8 and 20,000 people. In more underdeveloped countries where we don't have such a big infrastructure and we don't have such a number of appliances, of course, in the house, this could even go twice as much. But that's for you to know that we're talking a small city here, right? In this very simple model that we have, right? Like this. Now, one thing that we've seen when you model this type of scenarios is that you will always have to do some sanity checks, right? Regular Excel. So if you have, for example, the number of megawatts year divided by the total peak capacity that is installed, right? The typical numbers should be between these values, right? Between 1,200 to 2,400 hours a year, right? If you have something that is 3,000, that's wrong. So the model is wrong. That's totally unrealistic. 800 hours is too low, but maybe depending on the weather conditions, right? And something circa 2,000 hours is very reasonable. That means that for a sanity check, you can do that, right? Now, let's start with the first one. Right? Before we start with the losses, let's start with the first one, which is the number of sun hours. What I did, I generated, you see here, the equivalent full sun hours for the year as a normal distribution, 2050 and 120, right? So how do you do that? If you go to this Vos normal distribution, you can come here, right? Select the distribution like this. Let me show you. You will have that, and you can select, for example, a PER distribution, a normal distribution, a Bernoulli, etc. Any type of distribution that you like. We have more than 100 in ModelRisk. In this case, I use a normal distribution. So when you select and click View function here, right, I can check what were the numbers that they were used. You see, it's a mu of 2050, which is here, and a sigma of 120. So this is the number of hours that you will get, right? If you see here, it's between 1,600 to 2,600, like this, right? And as you could see, of course, is that you will have a lot of, the main ones are going to be here, right? That's the main idea. Right. So that's how you set up the distribution. When you set up the distribution, you start pressing F9, right? When you press F9, that's what's going to happen. Remember what I show you there is like you will have all these numbers that are changing. Let's focus here, right? These are the number of scenarios, and these are the different scenarios that you will get for the number of hours, like this, right? That's the number of hours per year. So each one of them is a different scenario, right? Because it's variable. You don't know until the end of the year, right? How many hours did you have? Then what that's going to happen is that you will have 4 types of losses, and these are the 4 types of losses that I wanted to show, right? Why is that? Because the solar panels, of course, are like it, and any electronic appliance of throughput like this is never going to operate under ideal laboratory conditions, right? So we will have a couple of losses in their use. One is temperature loss, right? Why is that? Because sometimes it gets too hot, so you have high temperature. Typical magnitudes of the loss, 5 to 10%. How do you do it? You put a normal distribution, maybe a mean of 7% and a standard deviation of 1 or 2%, which is here. You see? So you have this Vos normal formula that's going to be here, 7%, and I did it at 1.5%. What's the ideal here? And that would be my recommendation, is that you would always model as with the best practice in Excel. Don't hard code here. You will see that I will have a couple of hard coded ones, but my idea is always have these parameters, and you will see why. Right? So now we have our potential loss here, temperature loss, like this. Then we have soiling loss, like this. Because you have dust, you have sand, you have pollen, you have pollution blocking the sunlight, right? Rainfall sometimes, right? Typical magnitude 2%. And what we did, we generated a triangular distribution here between, or a PER distribution we added, right? and I can change that, of 0.02, 0.04, and 0.06. So this is the minimum, the most likely, and the maximum, right? You can directly change that here. If I want to do a triangular, and I did it like this, I can change it. And now I have a triangular distribution like this. If you like to see how the numbers will be, you see, you can always come back and change it, right? You can always come back and change it, say I want a triangular distribution, or I want a pair distribution, any one that you need, right? Then we have a third one, is the inverter loss, which is here. It's the DC power must be converted to AC power, right? And this conversion is never 100% efficient. The modern inverters are highly stable, so losses are mostly design related, not random. And this is something to take into consideration, because the moment that you start doing Monte Carlo, and this is something that always happens to people that start doing this, is that we try to put random effects in everything, and this is exactly the opposite. And that's why I wanted to notice that the typical magnitude is 2 to 4%. We decided to have a fixed value of 2.5, right? But you see here, the inverter loss is deterministic engineering loss, right? Not risk. Maybe it's a little bit high or low, but not always you have to add a distribution, right? In this case, you see, I just added something that is totally static, which is great. So a couple of things that we have now. One, in the model, you can combine cells and formulas which are not distributions. That's one. Number two is that you can combine a normal distribution with another normal distribution, but now with a triangular distribution. You can combine distributions. That's great, right? Number three, and we're going to see in the availability loss, right? What happens here? Same thing. We have planned maintenance, forced outages, grid disconnections. I mean, it's a system that was created by humans that have so many moving parts, and typical magnitudes are from 1 to 3%, right? Again, the availability should be always between 0 and 100%. So what is it that you do when you have between 0 and 100%? You model with a beta distribution, right? That has an alpha and a beta, and that's called like the mother of all distributions. So you have a beta distributions there. Extreme outages are possible, right? And we use, for example, a ModelRisk 298, which is here. So you can go with the BO function here, and you will see the beta distribution that I have there, right? Like this. Right? So this is the amount of availability loss that I will have, right? So everything is here multiplied together. How do you multiply this? You multiply this in this performance ratio. Remember, the formula that I showed you before is that you have the installed capacity, right, times the sun hours times the performance ratio, which is this, right? And this performance ratio, it's not but the multiplication of all of this, right? 1 minus this times 1 minus this times 1 minus this, etc., like this. And then you have a performance ratio like this, right? And we'll see that we will be able to see what is the performance ratio during the simulation, right? So what happens is that we're going to be able to multiply the 50 megawatts that we have there times the number of hours times the performance ratio. We'll have like 90,000 megawatts here, plus we'll have this curtailment, and with this I finish, right? Is the grid-driven energy reduction, right? It's the intentional reduction of energy when you inject it to the grid, right? Even when the solar panel is technically able to produce a little bit more. Why is that? Because you have grid congestion sometimes, oversupply, grid stability, etc. You see that it's not like you just plug it and everything is ready. You have to regulate it too. So that's why this is not a technical, and it says there, it's not a technical failure. It's a system level constraint, right? So you have to multiply it like this. So it's, again, another normal distribution. So you see that all these things you can add up, and you can create as many constraints as you need with the model. You have now 9 distributions. So, and finally, you will have the, let me see here, finally, you will have the number that goes to the grid, right? So how it is that you do it? Now that we have the inputs, remember, we have the inputs here as the distribution. We have to set up the outputs. We set it up like this, Bose output like this, Bose output and the Bose output like that, right? You set it up, and then you run a simulation. You start the simulation with 1,000 iterations. And what we're going to see what is the output of the plant plus the output to the grid, right? So I can come here, click on results, right? And what I will see here, it's coming. Let's see, I don't want to see the scenarios yet. Here. What I have here is the cumulative, right, comparison of the energy delivered and the energy produced. You see? So let me show the legends, right? Let me show the legends here. You see, the energy produced, I'm sorry, the energy delivered is, for example, is less. You see here, and that's what I wanted to see, is less, that's why it's the red one, that the energy produced, which is the blue one, right? Like this. If I want, I can change that to a histogram, like this. Let me show you only the energy produced, like this. So this is going to be my energy produced, which is between, 78,000 and 96,000. You see that you can change, you can move this, but more or less the 5% is going to be between 79 and 96,000, right, megawatts, right? And the main idea is that after applying the performance ratio, right, this is my energy delivered. So you see what happens. It moved to the left, right? Why is that? Because we had this performance ratio that was being applied to it. And that's the nice thing about this, that you can visually see what happened to that, right? After applying the same number of hours, of course, in the sun hours, but with the performance ratio. So what happens here is that, of course, you can change this. You can change, for example, like this. Makes it very simple. You can go and say, well, I want to see what's my P80. I don't want to see these sliders because the sliders sometimes are not under any let me see, any condition. So I will say, I want to see my P80. I don't mind to see my sliders. You see that you have 92 megawatts here, but after the performance ratio is more like 89. So you lost like 2% of it. Right? And then this is something that you can do with the graphical capabilities of the software, which are great. Right? Now, what happens here? Because you might say, yes, but I want to see how is it that the performance ratio perform, right? I want to see my performance ratio because right now I don't have it. So what I have to do, and that's why I left it like this, I click here and I say I want an output that it's called performance ratio. Oops, like this. Performance ratio. Like this. Right? And then I have to run it again. So what's going to happen is that now that we added this new output, this performance ratio is going to be including all the calculations of it, and we're going to be able to see it. So if I click on results now, you see that now you have the performance ratio, and I can analyze the performance ratio like this, right? So the performance ratio is between, you see here, 78% and 90%. Right? So is this the right performance ratio for your plant? Is this the right performance ratio for what you're looking for? That's exactly what we need to see. Right? If you like, what we could do, we can say, well, let's insert a new tornado chart and analyze the performance ratio, which are the main, in this case, see here, you see, which are the main variables that affect the performance ratio, like this. For example, here, I would say the main ones are the temperature loss, the availability, and the soiling loss. You see, like that. And the nice thing about this is that you can see the sign, which is negative, of course. That means that they are going to push the performance ratio to zero, right? And I can see, for example, only the first 5, and I see that between the first 2, the availability and the temperature loss, I have more than 80% of the risk explained, which is great, right? I know that this could be done with the performance ratio as well. So you see that I just added one variable and I started to do all this analysis on the fly, which is great, right? That's the type of things that you can do with this model and with ModelRisk, right? That's the main idea. What else you can do? For example, you can go to this tornado chart and say, well, I want to understand Now, what is the tornado? I want to understand the key drivers, not for my performance ratio, but for my energy deliver. You see here? So you see that the main drivers, of course, as you would expect, are 77% of the risk, or the contribution to the risk, is explained by the sun hours. Plus, you have the curtailment. Remember the the variable that we added at the very end, plus the temperature loss and the availability loss, like this, right? So you see that it relativizes the weight of in this case the temperature loss, which is very high in the performance ratio, because the curtailment is higher and the sun hours are higher as well. So that's why you have the explanation here of the model. Now you can do as many. Let me see here. I'm going to insert an additional one, for example, another histogram, right? And I can say I want to see all of them together, like a box plot, like this. I want to see the availability loss, the inverter loss. Well, the inverter loss didn't have anything. The soiling loss, the temperature loss, like this, right? And I'm not going to see the energy delivery because it's too big. You see, now I can see the different distributions of the loss, like that, even the curtailment, like this. So with the box plots, I can see it like this, or I can see it like a whisker plot, like that. So it's very nice. All the graphical capabilities are outstanding there when you use ModelRisk. So now you see that with this very simple model, we started to see and to analyze each one of the different variables, right? Now, what else you can do with this? Because you can say, well, what happens if we are not yet building the plant, but just analyzing some scenarios? So what I did, I created these sun hours, right, for each one of 3 different setups or setup of scenarios, like pessimistic, regular, and optimistic. And what I did, I used, for example, for the pessimistic, I'm going to do it, I used what I called a distribution fitting. So I took samples from maybe some potential or closed regions, took it there, go to distribution fitting like this. So here I have the samples. And I say, you know, I want to compare several distributions that are compatible with mine, and then I'm going to get the best distribution to it. That's a distribution fitting, right? So this is going to give me a ranking of the best distributions, like this. For example, this is a normal distribution. And what you can do, if you like, you can compare, for example, a gamma, an airline distribution, a log normal distribution, etc., that you can analyze each one of them, meaning that you will be able to validate if the distribution that we have here, you see a normal distribution, a log normal, or a normal distribution, are the best. So what I did as a next step, you see that now we have our main initial model, right? The initial model has the energy that's going to be produced, the energy that's going to be delivered. We analyze the performance ratio, we analyze the main drivers in the ratio, and then we analyze the main drivers in the output, in the energy delivered. And now what I did, I created a scenarios one, like this. So I created 3 models, like this. Each one of them has a different distribution for the hours, optimistic, regular, pessimistic. The rest are exactly the same distributions, you see? I mean, they are going to oscillate and be different, but it's the same. I didn't change any parameter for any of them. The only one that I changed is here, right? When I run the model, one important thing that happens when you use ModelRisk is when you run the model, all the variables are analyzed, all the variables are sampled and simulated. That means that I've already have this information here. And what I can do, let me go there, and you will see is that I can go, for example, to this histogram, but this histogram, I can check and say, you know, I want the histogram for my scenarios. You see? You have my model, which is this model. And I saw also my scenarios here. So, for example, for my model, I'm going to close it because I don't want to do it. I want to compare the scenarios one. So imagine for the optimistic, I want to see the energy delivered. The energy delivered for the optimistic is going to be to the right, right? Then for the pessimistic is going to be to the left, and for the regular is going to be in the middle, like this. So it doesn't help, you see, when you have histograms one on top of the other. Normally when you have 2 is more than enough. So you can change that to a cumulative ascending, like this. right? So you can see what happens when you have more than one scenario, and you can create scenarios on the fly like this. I just copy the model, replace the distribution that I was going to use in the normal in the sun hours. That's everything that I did, and then I run it. And then what I created is a set of scenarios that I can analyze like this and say, for example, my PAT. Let me change the factor here. Give me 1 second. Let me change the factor so it has not a scale factor of 10 to the 4th, but maybe in the thousands, like this, you see? So now you have that my P80 for the optimistic one is 98 gigawatts. For the pessimistic it's 94, and you see for the regular is 91. So it's between 90 and 98, right? What you can do. The nice thing is that you can analyze all of them together like this, or you can analyze, remember that you can analyze them as box plots like this, or like whisker plots like this. You can analyze them however you like, however your crowd likes to analyze them too. Or if you like, you can generate, again, another tornado chart and say, I want to see what happens with the optimistic one. And in the optimistic one, what you will have, right? I'm just going to add the scenarios one, which are the main variables that you have. This is called the conditional mean tornado. And this conditional mean tornado is going to let you see that the curtailment for the optimistic one is the one that generates more, in this case, variability. You see that in this little red line that you have here is the mean of the total energy delivered, right, for the optimistic scenario. And these are going to be the main variables affecting it. If you like, in the tornado options, you can say, give me only the top 5. So I don't want to have all of them together because it's a lot of things going on. So you can filter that, right? Like this. Or you can change the type of tornado chart, like, for example, correlation tornado, like this. Or if you like the contribution tornado that we were talking about before, like this, right? And we get to the same conclusion, that the temperature and the curtailment are the biggest variables influencing the model. Right? So what we did, remember, we created a simple model. We added, for example, the performance ratio. We could validate and analyze the performance ratio for each one of them. But now what we did a comparison of 3 scenarios, and these 3 scenarios were the optimistic, regular, and pessimistic scenarios as well. Right? That means that if you're going to compare, in this case, locations where you're going to put your plan, you can do it like this. Of course, this is a very high level estimation, but at the same time, it will include some randomness that perhaps you don't do when you do some type of, napkin estimations, which are even less accurate, right? Another thing that you can do, and with this, I don't know if I have questions, right? But yes, it's going to have, we're going to be sharing the recording as well. Now, what else you can do here? And this is typical in these types of models, right? If you have, let me see here, we have the results, and we, if you like, you can write to me and I can share the slides as well. Very happy to do it. What if we add some simple correlation? Why is that? Because normally, the higher the number of sun hours, the higher the temperature loss. Remember, if you have very high temperatures, there's a decreasing effect in the panels. So if you have higher sun hours, that means that you will have a temperature loss. What I'm going to do, I'm going to go back to the first model, and in this first model, I added a correlation here, and this correlation, it's between, right, these 2 variables, right? This let me see here. Let's see if I have it. I don't have it yet, so I think that I can just do it again. So I can do it from the number of sun hours and the temperature loss, right, like this. I can say correlation bivariate copula, because we only have 2 variables here, right? And it's going to be, for example, 0.9. You see, it's very high, 0.9. I'm going to exaggerate a little bit so you see the effect. So that means that the higher the number of hours, the higher the temperature loss, right? Which is right. The lower the number of hours, the lower the temperature loss. That means that these two are going to be correlated, right? So I just insert that to the worksheet like this, right? These numbers here, if you want to know what is it that they represent the percentile. Remember that we have a normal distribution here and normal distribution there. So this 73% and this 87%, they represent where they are getting this sample from. For example, here this could be 0.80%, 87%, and here this is going to be 0.73. What this is showing us is showing that this is going to work in tandem, right? So if I generate a new sample, you see, if it's very high, the other is going to be very high, which is exactly what we wanted to do. Same thing here. If it's very low, it's going to be very low, like this. So what's going to happen, and this is very interesting, if I run the model, right? Let's run the model again, is that the results are going to slightly change, right? Why is that? Because now we are adding more of a reflection in reality, right? The reality is that you have that, so you don't need to go again to the scenarios. I close this, I go to the cumulative distribution, I close the scenarios, I like this, and I say, no, I want to see the energy delivered here, like this, right? And I want to see my P80. My P80 is 94, right? That's how many I'm going to get, right? 94,000. What is it that you can do here? You can do plus Bose sim percentile. From this, give me P80, and maybe equal to Bose sim max. What's the maximum from this? Like this. It says no simulation results because I need to run the simulation like that. Right? So what I'm going to do, I'm going to calculate the percentile 80 of the solution, right? Basically, how much we're going to do with the correlation, and that's what I'm going to show, right? Like this. This is with correlation. So, and what happens if I change now the correlations to 0, as we had it before? Oops, let me see here. As we did it before, like this. Right? So now I have correlation of 0. So what we will expect is that if the behavior is going to be totally independent between the variables, that's going to happen is that you will have less energy, right? Or more energy, let's see, but you will have slightly different results. So you see here, your P80 is going to be a little bit more, right? The estimation of the P80 is going to be a little bit more. Why? Because sometimes can be that you have a lot of sun hours, but at the same time, you're going to have very small losses, which is not true. The same thing here in the maximum, 103.1075. My recommendation, what's my recommendation? Because you might see, well, but this is not a big change. Of course, it's a small model and you have very little number of variables, etc. But if you can model these types of things when you have very straightforward relationships that you can actually include into the model, include this into the model. That would be my recommendation. Right? Why? Because this is going to be better than that. Right? At the end, this is saying that you will have less final throughput as a P80. And that's going to be very valuable for you. So why? Because you're considering one condition, remember, which was that you have a correlation there. When you have a very high temperature, you're going to have, of course, more temperature losses. And this is something that you need to include. We already did the sun hours, right? Use historical data for distribution fitting and generate 3 models, right? And compare all of them together. Right? So those were the things that I wanted to show today. You see that what we wanted to do, and just as a little recap before we let you go with your day, right, is that remember we started modeling with a normal distribution the number of hours that you have exposed to the sun. Then we added 1, 2, 3, and 4 losses that could be random or not. And remember that they could have different distributions. They could be normal, triangular. They could be straight numbers like this, like the inverter loss, remember, which was supposed to be an engineering design loss. Right? Then we calculated the performance ratio, which was the multiplication of all of them. And we added, remember, we added the performance ratio as an additional variable just by adding the Bose output. And then we could add and create, right, and create analysis of these performance ratios. So if you're in the, let's say, in the engineering side, you're not in the delivery side, but in the performance ratio, what is it that you can do there? And you can focus on the tornado chart of the performance ratio to see what you can improve or maybe lower, right? Maybe you want a higher performance ratio. Then we added in this case, the energy produced and the energy delivered, right? And we were able to generate with the results a lot of this information, right? So I tried to show you and showcase all these nice capabilities. For example, here, let's say that you want this graphic, and with this I will finish. You want this graphic to be updated every time that you run the simulation. I created a new sheet here, and I go to the link chart, right? And then you do new link chart, and this new link chart is going to create that automatically. Every time that you run the model, this link chart is going to be updated, right? So this is a lot of productivity and a very nice way of using ModelRisk as well. After that, we did two things, two what ifs. One, we added correlation, which was the one that I just explained. And number two, by using historical information from other areas, we created distributions for the tornado, for the sun hours, and created these scenarios here, like this, basically 3 models that you can compare, right? Finally, we created this report, and this report here, it makes use of Bose sim functions, Bose sim min, Bose sim max, Bose sim percentile, just for you to know. So for you to know that you have also the availability or the capability of taking a look to that information from Excel, right? So you don't need, like this, you see, you don't need to, let me eliminate that. Oh, here you go. Yeah, you have the min, the max, etc. You don't have to always use the graphics that come with ModelRisk if you don't like. You can go back to Excel if you like and do your own. Right? So these are the types of things that you can do with ModelRisk. We wanted to apply it to something that it's less usual, which is like a solar panel, and we're going to be doing more like energy, data centers and mining during these webinars that, remember, occur once per month, and every month we have a different model. Right? We have from one of the attendees, Eduardo says, do we have a checklist, decision tree, or any type of framework to follow when we're building a model? We can share that, definitely. We can share. It's an excellent idea. Maybe what we can do is in our next webinar, we can even showcase it and use it so you can see it.